Good afternoon, everyone. Just to introduce myself, my name is Adrian Winckles. I'm the Director of Cybersecurity, Networking and Big Data Research Group at Anglia Ruskin University in Cambridge. Some people also know me from my activities through OWASP in the UK as well. What I'm talking to you about today is one of my PhD supervision projects. Oops, there we go. One of my PhD students was doing their thesis on a botnet needle in a virtual haystack. This was effectively a mechanism by which you could capture botnet communications in virtualized environments, essentially within cloud service providers. Why cloud service providers? Well, cloud service providers are an essential building block for modern IT systems because they provide the back end for IoT systems. And cloud service providers provide a great hosting platform for botnet CNCs, that's command and control mechanisms. If you think of things like Amazon Web Services, EC2, if you can spin up a virtual machine or an instance in those environments, you can use them to host multiple command and control mechanisms anywhere in the world, sometimes for free, and if one gets taken down, you spin up a new one. Some of the interesting sort of spin-offs really from that work was from a malware detection point of view, from a investigative research point of view, cloud service providers provide things like tenant isolation and data privacy. If you have two different customers hosted on the same physical server, there has to be isolation between them. They can't see each other's data. And that means there's effectively an internal infrastructure that needs to be protected because it's part of an attack surface. So how do you go about recovering data in a virtualized environment effectively to identify that botnet communication? Traditionally, we would want to do things like packet capture. We'd want to capture everything and be able to determine and find the communication that we're looking for. This is, if you like, this is the searching for a botnet in the virtual haystack, because if it's akin to the old acronym, you can look for looking for a needle in a haystack. Finding that little bit of botnet communication in all that data is a difficult task, and capturing network traffic is a big data problem. So how do organisations effectively capture all the traffic in their organisation to be able to go about finding that communication? Essentially, what a lot of organisations do is they feed their data to a central collection point. They'll use individual switches, and they'll use what we call mirrored ports, where they copy all their traffic to it, and they provide a copy of all that traffic goes back to a central location where you can see everything that's going on. And this may include other sites within the company's wide area network, mirroring that traffic back to a central collection point. And then you provide a fat leased line or connection to your security operations center or whoever's doing your monitoring function, and then they analyze that data and make recommendations from it. The problem is, this means if you're using port mirroring, you're copying data, you're effectively doubling the amount of bandwidth you're using. It also assumes that you have the right type of devices that will copy traffic and be able to mirror it. It also means that someone has to pay for a very fat leased line or internet connection to your managed security operations center. Organisations like Darktrace famously do this sort of monitoring where you provide all your network data to one monitoring point, either within the organisation or via that leased line back to another organisation. Oops, going the wrong way. So has history given us a better way of having to capture all traffic? Because it strikes me that a lot of what you capture is wasted. Yes, storage is cheap, but I know lots of organisations that capture data and don't use it. Traditionally, in bygone days, we used to use things like simple network management protocol, but the information that MIBs provided made it very limited for the information that you could actually ascertain from communication. Things like syslog for collecting logs from servers, routers, switches was unstructured. You had to manipulate the individual events to produce anything meaningful. So in the 1990s, the Internet Engineering Task Force tried to tackle the problem by aggregating communication into what we call flows. And a flow, for simplistic purposes, is a source and destination IP address and a source and destination port, plus additional information if you wish to do, but that's the small tuple of information that's necessary to have a unique TCP/IP conversation. But when they first proposed this in the 1990s, it made no progress. Vendors weren't interested. So Cisco in 1996 went away and patented their own flow technology, which collected that information so you could summarize network communication. So they invented something called NetFlow. And NetFlow is proprietary. It's not an open standard. It is Cisco's licensed technology. Other people have attempted to copy it, but it is still Cisco's proprietary own. With that patent, they created what I've already said, but a 5-field tuple, which was source IP address, destination IP address, source port, destination port, and a protocol field to tell you the type of sub-protocol you were using in the TCP/IP stack. So an analogy you can make is if when you compare something like NetFlow to something like PCAP, PCAP is like the phone call, and NetFlow is like the phone bill. It tells you who you called, when you called, and for how long. It's summary information. But summary information can tell you a lot without collecting everything that you might not use. So there is potentially a technology that we can use in cybersecurity to maybe analyze attacks, maybe analyze other things. So if you think about flow technologies and how we can use them, flow technologies still use a probe-based approach. This can be a probe based on a router, a probe based on a switch. This could be a probe embedded in an operating system on a server or even on a client, as well as a dedicated piece of hardware and software as well. Those probes analyze the network traffic that goes past them. They produce a summary. That summary gets exported to a collector in NetFlow or in a newer technology called ipfix, which we'll cover in a minute. A collector then brings those aggregated flows together into a recognized format, and you can store them for further analysis by a security analyst in a security operations center or whatever. Cisco have actually created multiple versions of NetFlow. The most common one that most devices support nowadays is NetFlow version 5. 2004, Cisco updated NetFlow to NetFlow version 9. This is important because NetFlow version 9 introduced some key enhancements. Effectively, now there are additional fields and it could be used for more in-depth analysis. The problem with the original NetFlow version 5 was it had fixed fields. It couldn't be expanded. You could only record the information that the standard set up for it. It collected header information. It didn't look inside the packet. So it couldn't actually tell what the contents of the packet were. So it could be duped into thinking communication was something else. It didn't support things like MPLS, IP version 6, VLANs, and it was still based on sampling technology, usually in a 1:50 ratio. So the argument still went, maybe you've missed something. So what was built on top of this was a new open standard, agreed in 2013, something called ipfix, IP Flow Information Exchange. This is an IETF, an Internet Engineering Task Force open standard with its own RFC, so RFCs 7011 to 7017. This is a flow export protocol in its own right. It does not depend on NetFlow, it does not depend on vendors like Cisco. It's an open standard, so anyone can implement it. So you maintain vendor neutrality. No one dominates this sort of technology. It's extensible. What you can do now is NetFlow version 5 had a fixed number of fields. NetFlow version 9 had 79 fields, 104 if you read elsewhere in Cisco's literature. ipfix has 433 information elements. These are information that you can extract out of a packet today. But what makes ipfix more flexible is you can write a definition for any content in a packet called, if you like, an enterprise element. You can create your own. So you can create your own capture filters to pull out whatever information you want out of a communication flow. This means it can do anything that PCAP can do. And it has security built in by design. So this is an alternative technology to capturing everything with PCAP. Or it can be an additional technology. So what my PhD student did was create a template. What ipfix allows you to do is create a capture template. So I want to capture this data, these fields, out of a communication flow. So it's not saying I want, right, as the packets go past my analyzer, I want this packet, and this packet. I don't want that, I don't need that, I don't need that. You can discard. You can capture what you need. So if you have a specific analysis scenario, in our case it was botnet detection, if you know the fields you were looking for, you can pull them out and you can create a template that will just capture that and concentrate on that, therefore being more efficient, more timely, and effectively more productive for a security analyst, and they are able to quicker to respond. In the initial experiments we did, what we were finding was we actually had a huge data reduction. You could be capturing data all the time in terms of PCAP, terabyte, petabyte, storage requirements. With ipfix, with knowing the data that we wanted, we could reduce the data collection by 97%. So typical volume when we're doing experiments, so something almost approaching 100 megabytes, or looking for botnets, we could reduce with our technology using Botprobe down to 3 megabytes. The load, the analysis time, almost 3 minutes. With our probe technology, 0.2 seconds. So what we effectively did was we looked at the literature around up to about 30 botnet detection algorithms. So this is software that other researchers have produced for finding particular types of botnet. And they had identified the types of traffic that needed to be captured. And whether it was collecting data with NetFlow 5, or whether it was PCAP, they could say, well, this is the data you need to feed into the algorithm that needs to be captured. And these are the fields that will give you indication whether there is a botnet present. What we said was, okay, so we can capture that same data to feed into those algorithms. We weren't rewriting the algorithms, we were actually using someone else's research, their algorithms. we were doing the data capture piece that was feeding into them. And essentially, we identified 97% less data capture volume, faster capture. We didn't need to change the algorithms. In fact, before, the algorithms were using a mixture of NetFlow 5, so capturing those 5 tuple feeds, plus elements of PCAP data as well. So it needed 2 collection mechanisms to provide into the botnet detection algorithms. We only need ipfix. So what ipfix is doing, essentially, is allowing us to index PCAP. What it means is we can identify all the various parts of the fields. So we're structuring the data. That's what we're effectively doing. We're actually providing a structure for capturing data, which means we can be more efficient with identifying threats in the future. So, quick analysis of PCAP versus ipfix. ipfix, we just need an inline tap. What that means is we capture off the wire as it goes past. And akin to real time in particular. With PCAP, we often need span mirror ports. We need to copy the data that's going through switches and routers and replay it back to a central collection point. ipfix, we can embed capture code on any device. It could be on a router, it could be on a switch, it could be on a custom probe platform or an IoT device, quite possibly. The beauty of it is because we can minimize what we want to capture, we can target particular areas of security that various parties might want to address. PCAP captures data in plain text. ipfix, effectively, when it's got the data it's extracted from its capture, it's encrypted. It's protected against replay. In other words, in ipfix, there is security by design built in. When PCAP's captures back, there is no protection in there. I think the biggest advantage, as well as the reduction in data capture volume, is it is structured. Big data, threat data, is a modern problem. We have too much data to analyze. There's always industry, enterprise wants quicker response times. If you can reduce the data to identify where the threat is, you can have faster reactions. That means it needs to be easier to search. We mentioned the data volumes. It was held in terms of terabytes before. Now we're talking megabyte volumes. Before, organisations will argue, I need to capture everything. There's nothing that says you have to capture everything, or there's nothing that stops you capturing everything, just in case you miss. But you can apply a template using ipfix to capture pre-forensic type data, post-breach type data, as well as capturing everything. It could be a mechanism for you to filter down on the data that you've already captured. So it helps in cases of privacy, lawful inspection, where you only want to give certain data to law enforcement. You now have a mechanism for doing that. So, based on this research, we're looking at developing templates, sensor technology in a number of areas. Our original case study is botnets using Botprobe. We're also looking at a couple of interesting organisations at what we call our SMTP probe or spam probe, looking for spam generators in organisations that are using an SMTP feed and sending out spam from an organisation. We're doing some work with some service providers and some government departments looking at HTTP. So we're taking feeds off load balancers and looking at the HTTP traffic before it gets fed back into an SSL session. so we can pull the data out that the customer wants. And we're also looking at things like IoT probe, embedding this filtering technology in IoT environments for better security analysis. And we're also working in industrial control, critical infrastructure environments using embedding ipfix into SCADA to pull out the register data to compare and applying sort of machine learning to see if we can identify if there has been a register change, for example, that's been unauthorized. The point I'd make is if an attribute is present in a packet, then ipfix can pull it out. We can capture it. So what do? We can put ipfix exporters almost anywhere. We can embed them in end devices. We can embed them in IoT sensors. We can embed them in industrial control systems, SCADA environments. The code could go on conventional routers and switches or dedicated probes, depending on what an organisation requires. We could embed this potentially on an ASIC. So, yeah, software probes, we can provide endpoint protection, increased visibility with fewer probes, and lower capture volumes. Yes, there's an argument, storage is cheap, but part of the crime is if you store data and don't analyse it, it's almost wasted. People keep petabytes of data just because, thank you. And of course, lower capture volumes. Thank you very much, thank you. And essentially, it's something we can use at critical points in an infrastructure, or at one point in an infrastructure, if an organisation has the traditional mirrored port scenario and they want all the data to be at one point, we can fit into that as well. What's also important, we can create a template, and that template is valid at one point in time. But of course, your capture requirements are going to change. So one of the projects we're working on is something called adaptive capture. If you think of this scenario, we've got a stream of network traffic that we want to identify threats from. So, for example, data's coming in A to E. At one point in time, we want to filter and pull out items A, B, and E. However, in response to some external stimuli, a newly identified threat, some threat intelligence, a machine learning algorithm can say, okay, so in response to this threat, I actually need to change what I'm capturing. So rather than A, B, and E, I now want to capture A and D. I'm still maintaining my data reduction, but I can change what I'm capturing, what I'm looking for. And it can adapt to the situations depending on threats, what if your other internal security systems, intrusion detection, intrusion prevention, identify something, that could be fed into a machine learning algorithm that could change the traffic collection profile. So, what started life as a botnet detection and capture piece now becomes, if you like, a more generic threat detection. If you think about that in any cyber attack, there are three stages. There's the infection, the detection, and the response. The problem most organisations have is that the average time to detect a cyber attack is 205 days. This is what Gartner said in 2016. And the cost of a cyber attack is reputational as well as financial. Sometimes the reputation is something you don't recover back. So in essence, what is it that we're doing? If you think of all the data that you capture from a network perspective, often what you're looking for is obscured. So it becomes a classic big data problem. What we're doing is we're providing the solution to say, okay, so we can help you narrow the focus to identify where the threat is. So we're not going to, at the moment, analyse the threat, but we're presenting you with the data to say, this is where we think the threat is. Because we can take away the large data volumes, it means that security operations centre analysts can respond faster, and you can protect assets and business reputation more quickly. And it means, because we've got this template extensibility, which means we can change the template, we can write additional decodes to pull out and interpret the data in there. We can match any field in PCAP. We have a method of big data reduction, so we can do things like automated mitigation, legal interception. Law enforcement has a requirement for service providers to provide data in certain scenarios on suspects. We could potentially do pre-event forensics. You could have an accurate summary of what your network was doing before events occur, and you could keep that longer and be more focused if something happened. We can do the indexing piece, which means that any PCAP data you have, we can structure. So even if you wanted to capture everything, and there's still an argument that says organisations want to capture all the PCAP data for all the time in case they miss something, well, we can help with that because we can index that. So it makes your searching faster anyway. And you can write new detection algorithms because you can identify the pieces you want. So what we've done is not just for botnets, it's for any cyber security threat. So obviously we're interested in collaboration. We'd love to talk to you. Please come and talk to me. Thank you.